So today we see about problems on radiation. Okay, we already know what are radiation, so what are the radiation principles, what are the laws are involved in radiation. So we know that losses are Lorentz laws and Gibson's laws, Stephen Boltzmann. So we use HMT data book in 90 editions. The page number is 890, so 990. So we have a lot of uh, formulas related to radiations. Okay. So in this problem, we find out the emissivity factor. Yeah. So just you see the problem. In this problem, the gray surface is 900 degrees Celsius. We have the black and black body radiations and red body radiation. We have more radiations in the emission of radiation in black body. So in this problem, given a gray surface. Okay. So the surface temperatures are given, that is a 900 degrees Celsius. It is converted into Kelvin. Okay. So plus 2.273, we get the Kelvin value, and the maximum emissive power, that is a EB lambda max, the value is given, that is 1.4 into 10 power 10 watt per meter square. Okay. So what are the values that we find out? We find out the emissivity, and that is the emissivity of the black body, and wavelength is corresponding to the maximum intensity of radiation. Okay. To start the problem, this given value is given, that is surface temperature. So surface temperatures are given. Okay. That is T is equal to 9. To convert it into Kelvin plus 273, we get what 7,073 Kelvin. Okay. Then maximum emissive power, that is a maximum emissive power value. The maximum emissive power is also given. So that is the maximum emissive power. That is EB. So notations are very important. Okay. Only EB mentions the total emissive power, but in this problem we give maximum emissive power. Okay. So that is 1.4 into 10 power 10 watt per meter square. Okay. So what do we find? We find out the max emissivity. So that is the emissivity of the body, that is the emissivity, and the wavelength, that is a wavelength with respect to maximum intensity. So lambda max. Okay. So we find out the first we find out emissivity, then we find out the lambda max for the maximum wavelength. So the first solution. So we know that the maximum emissive power. So maximum emissive power, that is a EB lambda max. Formula for maximum emissive power, that is obtained from Stephen Boltzmann's law. Okay. That is C4 into T power 4. That is sorry, T power 5. Okay. That is the fifth power of surface temperature. So in this Stephen Boltzmann's law, we know that the EB is equal to sigma of Stephen Boltzmann constant into fourth power of temperature. We obtain the maximum of the emissive power, that is C4 into T fifth power of surface temperature. So we solve the equation. We know that C4 value from data book are get the constant value, that is a 1.307 into 10 power minus 5 watt per meter square Kelvin power 5. Okay. So the substitute C4 value, we get C4 max equal to, that is a C.307 into 10 power minus 5 watt, sorry, to the fifth temperature, that is the surface temperature, that is the power of 1172. So substitute the value, we get EB lambda max. That is a, so just to check it, the maximum values are is correct or wrong. So EB lambda max is equal to 1.4 into 10 power 10 watt per. This value for algorithm. So next we find out the emissivity. So we know that emissivity. So emissivity is the EB lambda max, that is EB lambda is given. So this value is not there, that is the value for solve the equation we get 2.90. Sorry, this is a, so this value is already given, that is from problem. We solve the equation, we get the another value of maximum emissivity. So given value divided by, we get the emissive power, that is a 2.90, that is into 10 power. If we solve the values, we get that is from 1.4 into 10 power 10 divided by 2.9 into 10 power 10. We get the emissivity, that is 0.48. So that is just this layer is, I think, wrong. So we solve the equation, so 1.37 into that is C4, we get the 2.90 and into 10 power 10 watt. We related to the given maximum emissivity power, and we get the sum of maximum emissivity power. So the ratio of this maximum emissivity power, we get the emissivity. Okay. So next we find out the lambda max. We know that the relationship between maximum wavelength to the surface temperature we use from HMT data book. This page number is 90. So means displacement law, that is a lambda max, that is a into T into 2898 per meter. This is a form of this displacement law. So we find out the maximum wavelength. Okay, so we know that surface temperature, the values are the constant values given. That is a critical emissive. Okay, so that is a lambda max. So the wavelength is equal to 2898. We convert the micrometer into 10 power minus 6 divided by the temperature. Multiplication is within the temperature guidance angle. That is a 1173. Okay, to solve the equation, we get maximum wavelength, that is, so we does not use 10 power minus 6, we get 2.4 into 10 power minus 6. Okay, so then we convert it into 2.4 into 2.4 in micro. Okay. So we get the two values, so emissivity and maximum wavelength. So in this problem, we use a HMT data book as a page number is. So next problem, we find out the surface temperature and the emissive power. Okay. In this problem, we have given the wavelength, that is the maximum wavelength intensity wavelengths are given. Okay. So the first we write out the given data. So that's wavelength are given plus 0.5. Okay. We convert into 0.5 into 10 power minus 6 into meter. Okay. So to find the value of surface, that's the first value, the surface temperature. Then we find out the emissive power. So surface temperature T and the emissive power, we know that that is something. So according to Wien's displacement law, HMT page number, laws data from HMT data book page number 90. So this is 90 for 9th edition and 82 for 8th edition data. Okay. So the formula is given for Wien's, that is Wien's displacement. Okay. So that is a lambda max is into 2. So last problem we can use this value. So 2898. Okay. So the values given as an intensity, that is, it gives a maximum intensity. So we taken as a lambda, that wavelength as a maximum wavelength. Okay, so taken as a maximum wavelength 0.5 into 10 power minus 3. The surface temperature we does not know. Okay, so surface temperature we does not know T. And then the value was 2898. So we now the micrometer is 10 power minus 6. Okay, we solve the equations, we get temperature. That's the surface temperature 2898 into 10 power minus 6 divided by 0.5 into 10 power minus 6. Okay. So we solve the values, we get the temperature, surface temperature, we get a 5, we get a 5000 something, 5800, 5800. We find out the first result, the surface temperature. Next, you find out the emissive power. We know that the relations between temperature and emissive power, the formula Stephen Boltzmann. Okay, so this formula is also from HMT data book, page number 82, from HMT, page number 82 for 8th edition, 9th for 9th edition. So we can use a 9th edition data book. Okay. So the formula for Stephen, according to Stephen Boltzmann's law. Stephen Boltzmann's law. Formula is given as EB. That is a emissive power equal to Stephen Boltzmann constant to fourth power of surface temperature. Okay, so we know that there's sigma values. This is a constant value. There is no changes in that. So sigma is equal to 5.67 into 10 power minus 8 watt per meter square Kelvin also. Okay, this value is also in same page. Okay, so just we substitute the value. We know that surface temperature. So we find out the emissive power. The sigma is a 5.67 into 10 power minus 8 into, that is a surface temperature given, that is a 5800. Okay. To solve the equation, we find out the emissive power. So we solve the 5.67 8 into 5800. To solve it, we get the value of emissive power is 64.1 into 10 power 6 into the watt per meter square. Okay, this is the second value, that is a emissive power. Okay, so finally we find out the two results. So the second result is just we know at the end of the problem, is just write the result. The surface temperature is a 5800 Kelvin, and the emissive power, that's EB. So don't confuse between EB and EB lambda. Okay, so EB lambda is a monochromatic emissive power. EB lambda max is the maximum emissive power. That is EB is the only the total emissive power or emissive power. Okay, so that is a 64.1 to 10 power 6 watt per. Okay, so this is a simple problem. It's asked in 2 marks or 4 marks questions. Subdivision questions are in this problem. So next problem, this is just long problem, but we can use simple methods. Okay. So in this problem, you find out the 5 results. It has to be given the values is just temperature. So what is the emission of radiation temperature is given? That the back body temperature is 3000 Kelvin. Okay. So just we note the given data. This problem, the surface temperature is only given, that is 3000 Kelvin. Okay. So in this condition, also given in this first condition, we find out the monochromatic emissive power. The lambda values is given. So what is a monochromatic emissive? Already told you, the lambda is a monochromatic emissive power and wavelength of maximum. So that means lambda max. Okay. And maximum emissive power is a EB lambda max. And total emissive power EB. Why you mention the notations are use the formulas in data book. The notations are very important. Okay. So in this problem, calculate the total emissive power the furnace is assumed as the real surface having the emissivity. So emissivity values are given. Okay. So we use the emissivity, we find out the total emissive power. So that is a we find out the emissivity with respect to real surface. Okay. So first we find out the monochromatic emissive power. Okay, so these are the to find data to find these values. Okay, so directly go on solution. So the we find out the first EB lambda, that is a monochromatic emissive power. Okay, so from HMT data book, the page number is 90. So we also all the values are from used in this page number. Okay, so we find the first value, that's monochromatic emissive power. Use the relation between monochromatic emissive power and the lambda. So we give the lambda value, that is a wavelength, and a monochromatic emissive power. So EBY and EB lambda, we related this value, we get the law like Planck's distribution law. If use a Planck distribution law. Okay. The law is a EB lambda into C1 lambda power minus 5 divided by E power C2 divided by lambda T minus 1. Okay. So use this formula, we get the C1 and C2 values also given in this page numbers 890, same page number. The C1 and C2 values are given. The C1 value is 0.374 into 10 power minus 15. That's a watt per square, and C2 value also given. That is a 14.4 into 10 power minus 3 meter Kelvin. Okay. So we are next we find T values also now, whether 3000 Kelvin, then that the wavelength are needed. So the lambda is 1 micrometer. That's mentioned as a 1 into 10 power minus 6 meter. Okay. So we put the value C1 and the C2 and the lambda values and T values is 3000 Kelvin. That's given like that. Okay. To solve the equations, we get monochromatic emissive power. So that is the first value, EB lambda, that's a monochromatic emissive power. We finally find out, we get 3.10 into 10 power 12 watt per meter square. Okay. So we find out the first value. So next we find out the wavelength. So we know that wavelength at maximum. Okay. So that is the maximum wavelength. So we find out the relations of maximum wavelength and temperature. So the relation between maximum wavelength and temperature, we follow the law is Wien's displacement law. The from Wien's displacement law, the formulas are given, that is a lambda max into, there's a maximum wavelength into surface temperature into equal to 2898 micrometer Kelvin. Okay. So we find out the maximum wavelength, the temperatures are in now, the values are there. Okay. So lambda max equal to 2898. We convert the micrometer into 10 power minus 6 divided by the temperature multiplication. We go to the right hand side, we get the division, that is a 3000. That is a 3000 Kelvin. Okay. So we finally find out the maximum wavelength, that is a 0.966 into 10 power 6 meter. Okay. So this is the second value. This is a second value. Okay. So next we find out the maximum emissive power. That is the maximum emissive power. So the formula for maximum. So our last problem is C. The formula for maximum emissive power. That is a EB lambda max is equal to C power 4 into T power 5. Okay. So C power 4 value we are in now. That is a 1.307 into 10 power minus 5, and the temperature, the surface temperature is 3000 over 5. We finally find the maximum emissive power is 3.17 into 10 power 12 watt per meter square. Okay. So that is the EB lambda max. Okay. So that is the third value. So next we find out the total emissive power. Fourth value is total emissive power. We know that emissive power, that is a Stephen Boltzmann law, that is according to Stephen Boltzmann's law. Okay. So EB, that is a EB is equal to sigma of T power 4. Okay. So we know that Stephen Boltzmann constant, that is a 0. Sorry, 5.67 into 10 power minus 8 watt per meter square T power 4. Okay. This is a Stephen Boltzmann constant. Okay. So substitute the values in this equation, we find out the total emissive power, that is EB is equal to 5.67 into 10 power minus 8, and temperature of surface is 3000 Kelvin power of 4th power. So we finally find out the total emissive power, that is a 4.59 into 10 power 6 watt per meter square. Okay. The values are fourth value. Okay. Next, finally, we find out the total emissive power with respect to real surfaces. Okay. So same formula should be used, but use the emissivity value. Okay. So emissivity into power of fourth power. So this also from Stephen Boltzmann constant law. So thus substitute the value of total emissive power of real surface. The emissivity is a 0.85. So 0.85 into the law of sigma, that is a 5 point Stephen Boltzmann constant, that is 5.67 into 10 power minus 8, and temperature, fourth power of temperature, then into 3000 power of 4. Okay. So emissive power, that's the total emissive power of real surface. We get to solve the values, we get 3.90 into 10 power 6 watt per meter square. Okay. So finally, we find out the fifth value also. Okay. In this problem, we find the first value is like that. Okay. So this there, and second value is there, and third value is there, and fourth value. Don't confuse the notations. Just EB means total. So the emissive power, and then EB lambda is a monochromatic emissive power. EB lambda max is the maximum emissive power. Okay. If you find out the real surface, just mention as a real. Okay. So in the next class, we see about the shape factors and radiation shield related problem.